All right, this is the last day of notes for this unit. We are talking about polyprotic acids. We briefly mentioned them before, so do keep in mind that when we are talking about these guys dissociating, that they dissociate stepwise. Okay, so one hydrogen at a time. So here's an example of that. Here's this H2A dissociating, giving up a proton, and then I take that product and I make it the second round where it loses another proton, and then I'm only left with A with a -2 charge. So one important point about polyprotic acids is that after the proton is lost, the next proton is lost much less easily. So it's harder to lose every time. So this means that the acid becomes weaker and weaker. So super duper 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 important. Let's talk about that too. So also their Kas get smaller. Okay, and remember, the smaller K we have, the less likely it is to dissociate, or doesn't dissociate as much, or just to a very, very small degree. So every time it loses a hydrogen, these Kas get smaller. The hydrogens are harder to lose. Okay, so really, in all reality, the first hydrogen that dissociates is the most important one. Okay, so what we're going to kind of see on the next page is we're going to do a stepwise dissociation of these polyprotic acids, and I'm not going to lie, it's kind of intimidating, but it's going to be okay. So here is an example of a polyprotic acid, and notice it can go both ways. So this was H3PO4 was the acidic parent, and when that acidic parent dissociated, I had H2PO4 minus. But then this can act both ways. It can act as an acid and donate a proton, or it can act as a base and accept a proton. So here it is donating a proton. Okay, this is written incorrectly. That's not supposed to be there. That too. Actually, supposed to be the charge. Yeah, that too is supposed to be over here. Okay, or it can act as a base, like I said, and accept one where I get my weak acid parent back. So this is an example of amphoteric behavior where it acts like an acid and a base. So when it asks which one will occur, both will in reality, but the one with the larger K is the only one the only reaction we have to deal with. Okay, so that's really important because I'm pretty sure, no, I'm not pretty sure, I know it's on your test. So I would pay attention to that. All right, this next page, really, we're just going to skip it because it shows you why the first proton is the only one that matters. You're never going to be asked to do anything like this, so we are skipping this page. Yay. Okay, so here we go. All right, so I'm going to draw some lines to kind of make this a little bit better. Okay, so on the right side is where I'm going to work first. What we do have to figure out is they've given us a 0.1 sodium something, I don't even know what that's called, solution. This is a salt, so we have to figure out who the parents are, and then we got to figure out how this is going to behave, because remember, this is a child of a polyprotic acid, so we've got to figure out, is it going to act as a base or an acid? So the parents here have a strong base parent, and I have a weak acid parent. So remember, when we do salts, the salt, or the part of the salt that has the weak parent, is the one that we add to water. Okay, so this is a weak acid because there's only one more oxygen than H. So what I need to do is write out all of the dissociation equations for this weak acid. So, got H3PO4 dissociates one proton at a time. Okay, the Ka for this is going to be called Ka1. Okay, then I'll take that last part, make it dissociate. And then I'll take that last part again. Okay, this will have a Ka2 and this will have Ka3. Okay, and make a little side note here, the Ka of H3PO4 is 7.5 times 10 to the negative 3. Okay, so really the only one I'm worried about is this H2PO4 because that's the one that's a part of my salt. And what I need to do is I want H2PO4 as the reactant. So here I'm good. But here I'm going to have to flip that one. So I'm going to come down here and I'm going to focus only on those two because those are the ones that have H2PO4. So here I'll have H2PO4 minus. Okay, so basically right now I'm taking that first equation and I'm flipping it. Okay, and okay, so here the H2PO4 minus accepted a proton. So here is and this tells me that the solution is basic. So this was that ion acting as a base. All right, or I can have the second option where it will act like an acid. Actually, let me move that down a little bit. There's some more work I gotta do. Okay, so on this example, it is donating a proton. Okay, so here it is acting as an acid and a base. All right, so now let's look at those Kas. Let's do them, I guess we'll do them in black. All right, so remember I flipped this one, so this was that Ka1, but this tells me that I have to have Kb because I have a basic solution in the end. So Kb is Kw divided by Ka. So when I do that, I've got 1 times 10 to the negative 14th divided by 7.5 times 10 to the negative 3. That was my Ka1. And when I do that, I get a Ka of 1.33 times 10 to the negative 12 for that equation. So that's my Kb for equation 1. Here, usually what they do is they give you a table. I have included a table of these polyprotic dissociations in your notes. It's kind of hard to see, but they'll give you any Kas or Kbs that you need on the test. So Ka2 I'm getting from the table, and it is 6.2 times 10 to the negative 8. All right, so again, we want the one that has the larger K. So which one is more likely to proceed in the forward direction? Okay, that's my larger K, which is this equation. So once I do that, now I just treat it like a normal rice table using the equation that has the bigger K. All right, so I'm going to do my rice table with the equation that I just came up with. So ooh, that's super ugly. H2PO4 minus plus water, double arrow, HPO4 minus 2 plus H3O plus. Okay, I get to cross out water. They told me I had a, finish that, a 0.1 solution, none of that to start. Shift towards my zeros, write in what I have. Remember, I get to declare this negligible because I do have K, and when I do that, I can come down here, I'll write my equilibrium expression, so K, writing it in terms of Ka because it is acidic. And I got H plus, HPO4 minus 2, and then H2PO4 minus 2. Okay, and then I just plug in what I know. So I know Ka, and I have that. So X, which is my hydrogen ion concentration, ends up being 7.87 times 10 to the negative 5th moles per liter. This problem did ask for the pH. Okay, so I'll do the negative log of my hydrogen ion concentration, and I'll get a pH of 4.1, which makes sense because it is an acidic solution. All right, next problem says determine the pH of a 0.1 solution of sodium, but now it's with HPO4 instead of HPO2, or H2PO4, sorry. So, completely different one that we're looking at. I'm not going to rewrite all of these dissociation equations, but I'm going to do our typical stuff. So, sodium and HPO4 minus is what it would break down into. Strong parent here, weak parent here, that's what we want. So that's the one we're looking at. It's just that it is a polyprotic acid as the parent, so we have to dissociate stepwise. Okay, we're going to use these same equations, but instead of me rewriting them, we're just going to look at the ones from up there. So we are trying to focus on HPO4. So we're looking here and here. When I go and write down my equations for HPO4, okay, I want HPO4 with the minus 2 charge, I want it as a reactant. So that first equation, it's not as a reactant. And again, we're writing all of these out to figure out if it's more likely to act as an acid or a base. So I'm going to go ahead and write this. Got HPO4 minus 2, so we're treating it just like we would for salts because it is a salt. And I get my double arrow, H2PO4. Oh no, I'm going to run out of room. I'm going to need to write smaller. HPO4 minus 2 plus water yields H2PO4 minus plus OH minus. So this is HPO4 accepting a proton. Okay, when it accepts a proton, it's acting like a base. So I get a basic solution in the end. Okay, now I want to write it acting as an acid. Okay, so it's going to donate that proton, making this solution acidic. Okay, so now let's look at the Kas. So this is a basic solution, so this is technically the Kb. I can find that by dividing Kw divided by Ka. Okay, and we already know the Ka1 for that equation, which is, the Ka2, because that was the second one. So I'll do 1 times 10 to the negative 14th divided by 6.2 times 10 to the negative 8th, which will give me a Kb of 1.6 times 10 to the negative 7. Okay, and then this one is just straight up the Ka3 from that last problem, so 4.8 times 10 to the negative 23. Okay, remember the one that's more likely to proceed or more likely to occur is the one that has the larger K. Okay, the one that has the larger K is this top one. Oh, let me circle that in red. Okay, so then I'm going to take that equation and I'm going to use it in my Rice table over here. Okay, so HPO4 minus 2 plus water. Ooh, that's ugly. Okay, so it's more likely to act as a base. At a 0.1 molar solution of that, water gets crossed out. None of this. Alright, my expression, products over reactants. And then I plug in what I know. So I do know my KB, 1.6 times 10 to the negative 7, x squared over 0.1. X is my OH concentration, which is 1.26 times 10 to the negative 4. From that, I can take the negative log of that number and get my POH, which is 3.9. And then I can subtract that from 14 and get a pH of 10.10. Yeah, 10.10. Alright, this is the last little bit. This is super important. This is definitely on some quiz or test or both. So this is talking about strength of acids. This top one is talking about binary acids. Okay, so remember those are ones that have two elements. So it says the strength of binary acids are determined by the size of the anion. The larger the ion is, the more spread out the bond is, therefore the more easily the acid ionizes. So here they've given you a comparison. Okay, remember all of these elements, iodine, bromine, chlorine, they're all in the same family. So basically what they do is they kind of have a tug of war with this hydrogen. So the longer the bond, and that means that a long bond is a weak bond, which means we are going to dissociate better. Okay, and that bond is long because the anion is big, which means the distance to the nucleus is far. So chlorine is the smallest out of all those. It's still smaller than fluorine. Okay, fluorine's considered a weak acid because fluorine's so small, so the attraction between the nuclei, between hydrogen and fluorine, is very, very strong because fluorine's a small atom, and as we go down, we get bigger and bigger. So that means that chlorine is the smallest out of these, but bigger than fluorine. Then I get a little bit bigger with bromine, and then I get a little bit bigger with iodine. So the attraction's not as great. So iodine's actually the strongest out of those, or iodine with hydrogen's the strongest acid out of those three. Okay, so then I have ternary acids. Okay, and more specifically, we're talking about these oxy acids. They don't have a hydrogen directly attached to the central atom, so a different effect is at work here. There can be two reasons for acid strength in these ternary acids. So the first thing is that you have a different number of oxygens on an acid having the same central atom. The greater number of oxygens, the stronger the acid. So they've given you this example here. Okay, and again, so more oxygens equals a stronger acid. Our ternary acid rule is that you have to have 2 more oxygens than hydrogens for it to even be considered a strong acid. So let's kind of compare these structures. Okay, so there's the 1 oxygen, and then here is get one that has 4. Okay, so this guy he is a lot more electronegative. It's a larger molecule overall, and it likes to spread out that negative charge. Okay, so it's actually a little bit more stable with all those oxygens, and it's more willing to give up this H because it's stable elsewhere within the molecule. And to be a strong acid, that's the number one thing that you have to be willing to do as a molecule. You have to be willing to give up that hydrogen and dissociate or break apart for you to be considered strong. Okay, let's look at the other rule. It says a different central atom on acids having the same number of oxygens. So here I've got HiO3, HBrO3, and HClO3. So the reason that chlorine this time with these 3 oxygens is stronger is because chlorine is more electronegative than the rest, and it's happier alone. Okay, it doesn't even want to have that hydrogen, so it's more willing to kick it off. Okay, so it's the opposite of binary acids. Okay, like I said, this is going to be on a quiz or test, so make sure you're familiar with these rules. So again, binary acids, the bigger the atom that's bonded to the hydrogen, the stronger it is. The more oxygens you have, the stronger it is. And then if I'm comparing the same number of oxygens with different central atoms, the more electronegative atom is the one that's stronger because he's happier alone and more likely to dissociate, because you've got to dissociate if you want to be a strong acid.